So far throughout this course, we've talked about all the parts of the processor. Each part takes a certain amount of time for the electricity to flow through. And then when we have an instruction running, we have a certain set of steps. Like, for example, the first step might be to fetch the next instruction. The second step might be to decode the instruction we just fetched. Based on what's being decoded, we might have to, in a third step, latch data that's going to be entered into the arithmetic logic unit. The fourth step might be to perform some type of mathematics. Take two numbers and add them together and get a result. And the fifth step might be to take that result and write it back to a register or out to memory. So we need a piece of equipment that will say, okay, now do step one. Allow a certain amount of time to pass, now stop doing step one, do step two. Allow the same amount of time to pass, then step three, step four, step five, step 1, 2, 3, 4, 5, and keep doing that over and over. So this is typically called the clock of the CPU. So we're just going to chat about what the clock is and what the clock rate is. So when you plug a computer into an outlet, like an outlet in the United States, for example, we use 120 volts and we have 60 hertz. So the wavelength that is coming in, it's kind of like a sine wave. Again, I have a slide, next slide will cover that. It's kind of like a sine wave. It goes high, low, there's an oscillator that makes it go high, low, high, low. And for example, in the United States, they operate at 60 hertz. So 60 hertz means that it'll hit the high 60 times per second, which is relatively fast, but we want to be able to take that signal and make it, instead of an analog signal with curves in it, we could make it a rectangular, it goes high, then stays high for a while, then drops low, and keeps doing that over and over again. So what the first thing we want to do is be able to take the input signal, which is like the one in red is the way it's done in the United States, with this level of voltage and this frequency, 60 times per second. It hits a high. So what we'd like to do is we'd like to be able to have electronics that will take this signal and make it more square, like go very high and then go very low and then very high, because computers run on either the electricity is on or off, at different levels of power. Okay, so, and then in Europe and other parts of the world, I think some of you said in Saudi Arabia, you have both types of outlets in your house. So you could buy these adapters that will convert the European inputs to the American inputs. And this would be the one if you were to come to the United States and wanted to use your European equipment in the United States. You plug it into this converter. That doesn't convert the one signal into the other. It's just an electron, it just connects. It would allow your machine to connect to another machine. Then when you plug your computer in, your wires, this is the plug from the computer, it'll have one of these converters on it. Hopefully this says, the input could be 100 to 240 volts. So that's the low end of the United States to the high end in Europe. And it can do 50 or 60 hertz. So it could do the frequency of 60 per second, or it could take as input a frequency as low as 50 per second. So this pretty much would work anywhere in the world, this cable would. So what we want to do is we want to, here's kind of our goal. So let's just go back to our processor. We have a simple processor we've been using as an example throughout the course. So just a little quick refresher. The idea when you're running a program, your program is written in this section. So it's a series of 32-bit instructions. And we take one out of here and we load it into our 32-bit processor register. And depending on how the bits are set, the zeros and ones, how they are set determines which one of these wires turns on and off and does whatever action needs to be done. So what the first step we'd have to do is we would take our instruction and load it into this register. A second step would be now that the instruction has been loaded, and that first step takes a certain amount of time, depends on how fast the electronics are we have for reading and writing to this memory location. Then each of these wires, whether they're on or off, will activate another piece of equipment within our processor. That takes a certain amount of time for the electricity to travel along the wire and then run through the electronics, the AND and OR gates, to turn on or turn off whatever bits need to be turned on for the second step, which is decoding the bits that came into decoding the bits of the instruction. The third step is typically in preparation of a mathematical operation. We might have to take data in some of our registers and latch them or capture their values. These are now the inputs to the ALU. So based on the instruction, an instruction might say take the contents of register 2 and add that to the contents of register 4, and then when it's all added up, put the results in register 6. So in order to do that, we have to first capture register 2 and register 4, then let their bits go into the, maybe it's a ripple adder if we're adding two numbers together. That takes a certain amount of time, and the result comes out the bottom. And then we eventually take the result and put it in a memory buffer and send it out to memory, or write it back into one of our registers. So we have these different steps. On this processor, our clock, here it says clock subcycles. I don't know if you can see that. Clock subcycles, and it has 4 steps. Step 1, step 2, step 3, step 4. And since this was a really, really simple design, if you notice step 4, the final step, which is where we are actually writing data back to memory. During the final step, we are also simultaneously picking up the next instruction. So with this design, and maybe next semester I'll write a five-stage, redraw this picture but using 5 stages instead of 4. In this case, we're actually doing the fetch simultaneously with the write of the previous instruction. So I think it would have been a little bit more clear if this said 1, 2, 3, 4, 5. So maybe what I'll do next semester is just separate this step 4, break its 2 parts up into a 5th step. Okay, but forgetting about that for now, what we want to talk about today is what is going on inside of this box, the clock cycle. So the thing is, what we need is a piece of electronic equipment that will turn this wire on for a fixed period of time, then shut this wire off and turn the second wire on, so that this wire will be the only one on, and then shut the second wire off after the task, after we allow enough time for the task. So for example, task number 2 or stage number 2 of our instruction is to open up these 2 latches and let the value from the first step, let the registers that are inputting into these 2 latches to be selected. So the bits are coming through in the first step. The bits that are coming into the registers are done in the first step. And then in the second step, we turn this wire on, which allows these latches to open up and accept a new value. That has to be done after the values are coming out of here. Then the third step in this processor, step 3, turns this wire on. This is where we actually write to the MAR. This is where we open up to the MAR. So this would be after the results going through our ALU, which is also part of our third step. We can actually capture the output going into our MAR. Okay, and then the fourth step is where we write our data into the MBR, where we're going to write it back to memory. So anyway, what we want to just focus on today is what is going on inside this box. So since we have electricity coming in from the outside world, a wave like either the red one or the green one, we have signal coming in from the outside world. What we'd like to do is have one piece of electronics, and this is more for like electrical engineering students, if any of you major in electrical engineering. how to convert a waved signal into a squared off signal like this. So don't want to get into that right now, but let's just say we had that. So suppose we had a squared signal like this. So a clock pulse is coming in, and it's saying, you know, it's low, and then it's high, and then at a certain period it goes low, and then it goes high. So it's, you know, on, off, and this keeps happening. Okay, so if we have this coming in from an external source, one thing we can do, if we wanted to just have fun, is we can delay the signal. And so we can have a piece of electronic equipment that basically says whatever you put on this wire, the same thing will happen on this wire, but it's just going to happen a little bit later in time. So all I did here, just to show how silly we could do this, is we have a NOT gate and another NOT gate. So if I put a 0 here, coming out of this NOT gate will be a 1. I don't know if you can see, this is red and this is black. So we'll say black is off, red is on. So the 0 here becomes a 1, and then it runs to another NOT gate and becomes a 0. So whatever is here, 0 or 1, will show up here a little bit later. However long it takes to get through the resistors and the transistors within this NOT gate, then get through another set of resistors and transistors here, and then have the output come out. And I could string as many sets of 2 NOT gates together. I could put 100 or 1,000. And then all it means is whatever is here comes out of here, but with a delay. So if we decided to make this piece of equipment, and maybe going further, I'm just going to draw a cloud and say delay equipment, meaning it's electronic equipment and only serves one purpose. To have whatever signal's coming in here, 0 or 1, have it come out of here, but a little bit later in time. And we can make the delay as much as we want, as short as we want or as much as we want. As long as we can put equipment together that will have the same exact signal come out, but just at a later time. So we can do things like take the input signal coming in from our electrical outlet. So if we're in the United States, this would be coming in, this high would happen 60 times per second. We could decide if we want to, we can have it delayed, and we could really choose as much as we want the delay to be. So we could have it delayed, just slid over a little. So it's basically, it's the same curve, just slid over with a delay. So now we start to realize, okay, if we can delay things, then we might be able to do other funny things. Like, for example, we could take an input signal and have it run into an AND gate and have the same signal slightly delayed running into the same AND gate. And we only want the output here to be high if both of these are 1s. Well, when are both of these 1s? Well, if there was no delay, they would either, when the input is 1s, they'd both be 1s, and when the input is 0, they'd both be 0s. So the output would match the input if there was no delay. Actually, there'd be a little bit of a delay in the AND gate, so it would still be slightly delayed. But we could put a longer delay here, and what that would do is say when this is a 1, this one might take a little while for it to become a 1, so it'd be a little bit of a delay when we switch this to 1 before this turns into a 1. And then when we shut this one off, this would immediately shut off. So what we'd end up doing is having the highs. So here's our input signal. This is the signal coming into this wire. And this is the output signal, what's coming out of here. So not only do we get a delay, because there's a delay for the transistors and resistors of the AND gate, we also get this intentional delay. We throw it here. And we need both inputs to be on before the output could be on. So we get a shorter high, and it's also delayed. So the size of these highs get shrunk because we need the input and its delayed version to both be on. So this one goes on ahead of this one, and then this one shuts off before this one shuts off. So there's a smaller time when they're both high, and it's also delayed. So we could take this input with this speed, this many hertz, and we can have an output signal, same hertz, same number of highs per second would be the same, but they would be smaller. Then we could also do other things like make them longer, make the high part longer and the low part shorter, by using an OR gate instead of an AND gate. Now, if either one of these is 1, the output is 1, and the only time it's 0 is when you put a 0 here and then allow enough time to get the delays to turn both to 0 and have the result of 0 coming in. So we also, this should be a little bit delayed and have unusually long highs and very short lows. So if we can lengthen the highs, we could lower the highs. And more interestingly, this is the real important one. We can make the frequencies go faster. So let's say, for example, we had a delay here. So I kind of replaced the 2 NOT gates with just a cloud that says delay. We can kind of set our delays as much as we want. So if we took an input signal, so this is really this top part above this red line, it's a repeat of 2 slides ago. We can take an input signal and have it have shorter highs, slightly delayed. Now, what if we took any signal, and we decided, suppose we took a signal like this one with the very short highs and the very long lows, very short highs. The frequency, so it's important to understand, the frequency of the highs here matches the frequency of the highs here because it's getting its power from the signal. We just made the highs shorter and delayed. Suppose we took this as an input signal and we ran it through a delay where the size of the delay is exactly the gap between one high and another high. So right in the middle here, we would get this bottom wire would turn on right in the middle here. And it would also turn on right in the middle here. Then with this delay, we can take our overall clock input signal, generate this signal, then run 2 of these signals, one delayed and one not delayed, one coming into an OR gate and the other one not delayed, and then we can have twice as many highs from the original input signal. And this is what's very important because what we can show is we can take the outside signal, which in the United States is 60 hertz per second, and we can create a new signal which is twice as fast, 120 hertz per second. And we could keep repeatedly doing this over and over and over. Now take this signal and make it have twice the frequency of the previous one. And keep doing that over and over and over. So how many times can we do that? Well, it depends on the electronics in our delay. If we can find a way to have the input to a wire, have it come out an output with as small a delay as possible, but still a little bit of a delay, then that would be another level of granularity. We could break these highs down. So in case you're wondering, how could I plug a computer into an outlet in the United States which has 60 hertz, which means 60 highs per second, but my processor is, what's a processor these days, like 4 gigahertz, 4 billion cycles per second. How could I get that much speed out of the outlet here in the United States? And we just keep using this trick over and over and over to get as many highs as possible. And what's going to happen is every time one of these highs happen, once we get it out to 4 billion highs per second, what will happen then is each one of these highs is going to be this clock going, on the first high, this wire turns on. On the second high, this wire turns on. So on the first high, only this wire is on and these 3 are off. On this next high, the second wire is on and the first, third, and fourth are off. On the next high, the third wire is on and 1, 2, and 4 are off. And we're going to just keep going 1, 2, 3, 4, 1, 2, 3, 4 every time the input signal, the sped up input signal, hits a high. So what we want to do is we want to have some electronic equipment that will take this 60 hertz, or 50 hertz if you're in Europe, this 60 hertz input signal and turn it into an equivalent, 4 gigahertz signal. And then on each high we want to have one of the 4 wires turn on. So once we attenuate the speed correctly, what we can do is we can take in this very, very fast input. And this gets across the idea, but we would want to use better equipment, safer equipment than this, but this will get across the idea. If we have 4 AND gates put together, and the input is the clock signal, so when the clock signal is high, the lower inputs of all 4 of these AND gates are turned on. So then what would their outputs be? Their outputs would be whatever the high end was. So if we had one more piece of equipment, maybe an OR gate right here with a wire coming in where I can turn on a wire for one instance of time. If, for example, this wire was on, if for example, this wire happened to be on at the moment, and this clock pulse was high, that means the 4 lower inputs for the AND gates are all turned on. If this wire happened to be on after the clock, while the clock is high, this output wire will turn on, and since this wire is connected to the next input, this will also turn on. Now you might think, if we allowed enough time, every one of these lines would turn on, because this being on would let this one turn on, which would let this one turn on, which would let this one turn on. So if we turned one of these wires on, they would all turn on. But each of those wires turning on takes a little time. It would have to ripple through. And if we set the clock speed to shut off right before the ripple is completed, right before the electricity was inputted to here, and then we shut this wire off, that would make this go off, which would cause all the ones after it to be off. So what we would now have is this wire's on and these 3 wires are off because the clock just went out. When the clock turns on high again, if we set this clock speed fast enough to match this piece of electronics, when we turn it back high again, this input, which was left over from the last high, combined with this turning on, will make this wire go on, and therefore this wire will start traveling, electricity will start traveling into this gate, but it will get shut off before it gets outputted. And the previous one would shut off because it got its power from this guy being on. Well, this guy has just been shut off, so this electricity would then turn off. So now this one would be off and this one would be on. And as long as we keep letting the clock pulse, this simple piece of equipment would have the property that every time we hit a high, one of these wires would turn on and the other 3 would be off. Then when it hit the next high, the next wire would be on and the other 3 would be off. And it would work its way down to the bottom. When it finally gets to the bottom, it would work its way back up to the top. So as the clock is pulsing, every time it hits a high, we start off with this one going on first, this one going on second, this third, fourth, this third, this fourth. 1, 2, 3, 4, 1, 2, 3, 4. So here's kind of like showing after the first clock pulse, this is the outputs. So hopefully you can see these red ones are on and the black wires are off. And now here the red one is the second one, which is on. So we can have a piece of equipment that just keeps the pulse of the clock just keeps going, and every time it hits a high, a new wire turns on. So this would be why the fundamental design of the clock says that no matter what stage you're doing, the fetch, the decode, the read the inputs, the execute the mathematics, and the final step of writing the results back to memory, whichever one of those 5 steps, if it's a 5-stage processor, 5 stages to run each instruction, whichever steps takes the longest, we would have to set the clock pulse to be as slow as the slowest stage. Because the clock pulse is just going to keep pulsing at whatever speed we take the 60 hertz input and speed it up to. Whatever speed we speed it up to, and then we're just going to turn on a wire, next wire, next wire, next wire. Now, you could argue the case that if suppose one of the steps of one of your stages takes twice as long as the other one, instead of having, let's say, 4 steps, we can have a 5th step and just cut off one of the wires, so that would let one of the stages take twice as long. We could kind of play around doing stuff like that if we wanted to. But it's generally, that would never work if we started pipelining, because pipelining requires that stage 1 of one instruction is happening simultaneously to stage 2 of the next instruction, and therefore all stages would have to be the same amount of time. So we couldn't have variable amounts of time for different stages, slower stages getting more time. Okay. If we decided we wanted to slow the clock down, once we have a piece of equipment like this, what we can do is we can say, okay, we have a 4-stage clock, and we could just cut off 3 of the wires, and then this top wire will just go on, it'll go on with a high, and then while the 2nd, 3rd, and 4th one, they just stay low, and then it'll go on high again. So if we decided, if we had this clock, this piece of equipment running in our computer, if we decided that we needed some other piece of equipment just needs to have a high that is 1/4 the speed of the clock that's running our computer, we could just hook that up to one of our wires, or maybe every other wire, so it could be half the speed of the clock. Okay. All right, so just a couple of definitions. You probably hear these words all the time. A nanosecond. What is a nanosecond? So a nanosecond is a 1/1000th of a second. So it's 1 divided by 1 billion seconds. And what is a hertz? Hertz is 1 cycle per second. So like I was saying, the input in the United States is coming in naturally at 60 hertz, 60 highs per second, which is pretty fast, but not going to keep up with a computer. What does giga mean? Giga means 2 to the 30th. Right? So just a little review. 2 to the 10th is a kilo, 2 to the 20th is mega, and 2 to the 30 is giga, which means approximately. So I'm saying a little bit more than 1 billion. 2 to the 30th is a little bit more than 1 billion. So a processor with a speed of 1 gigahertz has a cycle pulse that hits high a little more than 1 billion times per second. Therefore, it can run 1 billion stages of an instruction, not 1 billion instructions. If it's unpipelined, it can run 1 billion stages, like fetch, decode, read, do the ALU, write the result back to memory. You do that many stages per second. So if an unpipelined instruction has 5 stages, then this processor can run a little over 200 million instructions per second. It can run 1 billion stages, but each instruction has 5 stages, so it'd be 1/5 as much. So when you're buying a computer and it says, oh, the processor runs at so many megahertz, that's how many high electric pulses there are per second, and each high handles 1 stage of an instruction. Okay, and then just for a little perspective, the first computers that were manufactured originally had processor speeds between 5 and 10 hertz. So they'd have to take the electricity coming in through the wall in the United States, which is 60 per second, and slow it down to like 1/10 of the speed. So that's what I was kind of talking about. We can take a signal and slow it down. We can take a signal and speed it up. But they had to slow it down because the equipment that was fetching from memory and fetching and doing mathematical computations, multiplying, dividing, that equipment was so slow they had to slow the clock speed down. And so as of 2011, I think this is still currently true, the fastest processor now is almost 9 gigahertz. So about a little, this should be over 9 billion highs, the pulse coming in. It's 9 billion highs per second, and then each of those could trigger 1 stage in your instruction.
Okay.